now we want this neural network we created to be able to learn, and therefore we are going to need two more ingredients. The first one is backpropagation, and I will split this section into smaller subsections, and the other one is optimization. So what we learned in the last chapter was that there is some mathematical quantity. In our case, it was the loss and also the accuracy that we have to optimize, and it tells us how well the neural network makes the prediction. So loss was the entropy, so how sure is about the how sure is the neural network about the prediction it makes, and the accuracy is tells us how often it made the correct prediction. But still, we have to tell the network somehow how to do that. And let us first of all take a look at our network and at the structure that we have now. So we have the input that we feed into the input layer, then we pass the information on to the activation layer, then there's another layer, and then at the end we will calculate probabilities in the softmax layer, and from these probabilities we will calculate the loss function. So I also want to show the equations again. So here that's the output of a single neuron, so it's essentially the sum of the weighted inputs, and then we add the bias, then we feed this into the activation function. This A just stands for activation, so it can be any activation function. In our case, it was just a ReLU. Then this output is the input for the next layer, and then the output of the next layer is the input for the softmax layer, which calculates the probabilities. And based from the probabilities, we can calculate the cross entropy, which is our loss function. So, and this is, so to say, the process that feeds the information from the input forward to the loss function. And that's why it's called forward pass. And what we want to do at the end is that we want to optimize the loss function. So we have to change the loss function, which implies a change in the softmax layer, because the soft function is a function of all the probabilities, and those probabilities are calculated in the softmax. So if you want to change L and we want to minimize it, then we have to change P. So it implies a feedback on P, which implies a feedback on the output of the last layer. And that, of course, implies a feedback on the weights and the bias, because the output changes if we change the bias and the weights. But it also changes if we change the input. And how can we change the input? Well, we change the input if we change the output from the activation function, and we can change this by changing the output from the first layer. So it just propagates back from the loss function to the end of our structure. And that's why it's called backpropagation. And what you see here is the full math, which looks rather confusing, very impressive. However, there's a trick. We can actually simplify this by looking at this conceptually. So that was very complicated, but it's what's really going on in the network. And now we have to understand how we change those parameters in order to minimize the loss. So how do we handle the backpropagation? And therefore, it makes more sense to look at this more conceptually, so not at very detail. Again, we have to look at certain schemes, what our neural network actually does. So we have an input layer, and we have the activation function. Maybe we have other layers in between, but at the end, we'll have a loss function, whatever this loss function is. This loss function depends on all these different parameters, on the weights, on all the biases, and also on the input, of course. Not the actual input in the first layer, because that's our input data, so we don't change this. But the input of the second layer has been generated as output of the first layer. So therefore, we also have the input I as a parameter. And when we change the loss, it implies a change in the activation function and also a change in the other layers and so on. But what is the overall goal? So we want to minimize the loss function, and the loss function looks very complicated. It's a high-dimensional object because it depends on all these parameters. So what we could do, however, is we can just freeze all the parameters but one and as if the loss function is, for example, one-dimensional function, so that we can actually plot this. And it might look like this. So we don't really know what the loss function actually looks like. But we have an idea. And it might look like this, for example, if it just depends on Wi. So we have maxima, we have minima, and the idea is that we reach the optimal value so that we reach a minimum here, which is hopefully a global minimum, not a local one, but I'm going to say more about this later. So if we just start with our first iteration, so we just have our random weights and biases, do all the forward pass, and then at the end have a loss function, we will have a certain value. So we have a corresponding weight, and which gives us a corresponding value for the loss function. But ideally, we want to find a minimum of the loss function. So we have to decrease the value. So we have to find a new weight, which gives us a smaller value for the loss function. So we have to kind of follow the gradient or the slope of the loss function. So we have to follow descent of the gradient, and that's why it's called gradient descent. And the equation is actually pretty simple. So if we have to follow the gradient, then we can immediately write down the equation that you see on the right-hand side. So we have the new value for W, and that equals the old value minus the gradient of the loss function with respect to the weight times a constant epsilon. And I want to explain more about this constant. But what does it actually do? So if we have our old value here in our plot, and if the gradient is negative, like in our plot, then we actually have to move from left to the right. So we have to increase the value for W. If you look at our equation, it does exactly this, because if dl dw is negative, and we multiply this with a negative constant epsilon, then the overall expression is positive. So the new value will be larger. So we move from left to right because the new value of W will be larger. And it's exactly what it does. So if the gradient is negative, it moves from left to right. If the gradient is positive, then we would be, for example, here, and we actually have to move from right to the left. Well, if the gradient is positive, then this number is negative. So our new value for W will be smaller than the old values. In fact, we are moving from right to left. So that's very simple. And as you see, mathematically, it actually should work perfectly. So the only thing that we need to know is the gradient. So the derivative of L with respect to Wi. And as I said, L is not only a function of Wi, it's also a function of all the other weights, the biases, and also the inputs. So we have to adjust all the weights, the biases in the inputs, depending on the corresponding gradient. So the only thing that we have to do is calculating the gradient. So therefore, we can calculate the change of these parameters of the learnables, like the weights, by calculating the gradient and multiply this with minus epsilon. And minus epsilon is the so-called learning rate because it tells us how far do we go from left to right, or right to left, right? For example, if epsilon is very small, then we move in very small steps. If it's very large, then we just perform a huge leap. So that's how fast we move along the gradient. In principle, all these optimization algorithms are more or less different versions of gradient descent. All right, so now we have our recipe, and now we just have to calculate the gradient. And of course, the loss function is not a direct function of W because, first of all, W is the weight for calculating the output of a neuron. Then we feed this into the activation function and so on. So actually, L is a function of A and a function of W and B and I. So therefore, we have to calculate the outer derivative and all the outer derivatives until we reach a derivative for W itself. So we just apply the chain rule. So we calculate the L, the A, because it also changes with respect to A, the omega, which is the output from the neuron, and then we have the output of the neuron, the omega, the Wi. So this is just the derivative of the output with respect to Wi. And if we look at the output, well, the omega with respect to Wi is just the input I sub I. And when we look at these factors here, these are just the outer derivatives. So this is how L changes with respect to A, which we see here. And this is how A changes with respect to L, with respect to the input. So these deltas we have here in our scheme are actually the outer derivatives, right? Because we want to change the loss. So the loss changes with respect to A. If we want to change A, we have to change the output. So we see how A changes with respect to the output omega. So those deltas that we receive here are the outer derivatives. So delta L is the outer derivative of delta A, and both are the outer derivative of delta W. So kind of pass on these derivatives and thereby performing this multiplication. So automatically performing the chain rule. And of course, we can do this for all the weights W, and also we do this for all the inputs and all for the biases. So the loss function, of course, is also a function of the inputs. So we just do exactly the same thing. So for I sub I, we still have the same outer derivatives. The only thing that changes is actually dl di, which is just W. So then we have just Wi. And we do the same for the bias. So the last part will be the derivative of the output with respect to the bias. And when we just look at this, then it's just 1. So that's why we have this expression times 1, which comes from dl dB. So now we know how to change the weights, the input, and the bias based on the change we get from the loss function. So the structure of the backpropagation is always that we receive an outer derivative from the previous layer, and we will call this d values. And then we multiply this with the inner derivative. For example, the inner derivative of A is delta A, and we multiply this with the outer derivative delta L. But delta A is the outer derivative with respect to the output of the neuron omega. So therefore, this factorization occurs actually by passing on the d values through the layer. So, and if we want to have the change of W, I, and B in the neuron, then we just have to apply these equations. So the change of W then we want to call it d weights because it's the change of the weights, is then inputs times the outer derivatives, d values, and we do the same for the inputs and for the bias. So the equation here, these equations in the red frame are just the equations that you see on the left-hand side. And again, why is it just 1 times d values, so not the product of both? Because we have the product of both here already, because it propagates through the layers. So we have delta L and delta A, because this is the d value we pass on to A. Then we multiply this with the inner derivative and pass it on to the neuron, which is then the outer derivative, and that's already the product then. So delta L, delta A. That's the reason why the d values here includes already the product of all the outer derivatives. So, and I also want to illustrate this in a bit more detail now that it really makes sense to you. So the key point is that we just have to apply the chain rule, and we have to propagate the derivatives throughout the network. And therefore, we always will add another method, and we just call it backward. So like the forward method, where we always multiply the inner derivatives with the outer derivatives from the previous layer. So for example, for a dense layer, that we have the IDW. So we just pass on the outer derivatives with d values. And then we create so-called d inputs, and we pass on to the next layer. So again, I want to illustrate this in a more schematic way. So we have these different layers, and then we have our forward pass. And at some point, we have to apply changes to our loss function. And that's the first D inputs. So that's the change of our loss function, for example, delta L. And that's already the first outer derivative, which we pass on to the next layer. Then we multiply this with the inner derivative. So it's a product of the first outer derivative and the inner derivative, which gives us a new product. And we propagate this product back to the next uppermost layer as D values again. And these D values are already a product from the previous layer. That's what you can see here. So we have the two derivatives here, the two outer derivatives. And then again, we have here inner derivative in the layer. And that's how we propagate all the derivatives from the chain rule. And we always multiply the outer derivative of the inner derivative, which is the next outer derivative for the next layer. And we again multiply this with the inner derivative, and so on. So in principle, you can just do this infinite times. There are some limitations to that. I will explain this later. But in principle, if we just maintain the same structure in every layer, if we just always set up a backward method with the same notation that we have an input that we call d values multiplied with the inner derivative, which is our d inputs, and it will serve as the input for the backward method in the next layer, and we call it d values, then we can always put those structures together and will always work. So the rule of thumb is based on the equation we derived earlier, always multiplying the outer derivatives with the inner derivatives and pass it on to the next layer as the outer derivative. So therefore, that's our backpropagation. So then let's do this step by step. So let's start with the dense layer, then let's take a look at the activation function and also the softmax layer and so on. So we're always gonna add now a backwards method for the backpropagation, where we just have the inputs as an input, multiply this with the inner derivative, and then take this as an output for the next layer. And in order to do so, we have, of course, remember the inputs. Remember, there was one equation where we have to multiply the inputs with the inner derivative and with the outer derivative. That's the reason why we want to save inputs in the forward method, because that's where they show up the first time. So we need this for the backpropagation. And now we add another method backward where we feed in the d values. So that's the product of all the outer derivatives, or the previously calculated outer derivatives. And then we calculate the changes of all the learnables. So for example, the weights, that's what we just showed in the equation before, which was just inputs times the values. And you see that's why we need inputs, because we just need it for calculating the derivative of the weights. And we calculate then the derivative of the inputs, which always makes sense unless it's the first layer, because the first layer gets the actual input. And of course, we do not change the actual input because that's our data. But if it's not the first layer, then we always have to calculate the inputs, the derivative, because that's that was the output from the layer which was above this particular layer. And of course, we do the same for the biases. So that was just multiplied with 1. And then we just calculate the bias according to this equation. All right, so that is our layer. So we have the init part that we have already, then we add the inputs to the forward part, and then we have the backward part. So it's actually pretty simple. So therefore, we are ready to go back to our user interface. And again, we want to open a new folder or create a new folder. So we just call it backpropagation. And of course, we also want to navigate to this folder. And also save everything in this new folder. All right. So let's start with the dense layer. So the init is perfect the way it is, but in the forward part, we have to save the inputs. So we just add self the inputs. All right. And then we have to add the backward part. And that's in principle what we have to do now for every class. So the input for the backward part is d values, which is just the derivative, the outer derivative that comes from the layer which is below this current layer. And then we have to calculate the derivative for the weights. Which is then just np dot. And according to the equation we derived, so just remember that's the derivative of the loss function with respect to the weights w. And if we just perform the derivative, according to chain rule, the inner derivative gives us self inputs times the values. And in order to make sure that the dimensions and the shape fit, you can actually write it down or just try it, and you will see we have to transpose inputs so that it works. And then we also want to change the inputs. If it's not the first layer, and that's np dot d values times the weights. That's it. And then we just calculate the change of the biases. Which actually would be also a dot product, just the values with a vector containing ones. So we can just sum up the values. So we can just say np sum. And remember in the derivative, it was just the outer derivative times 1. And of course, we are working with matrices and vectors. So it's not just for a single neuron, it's for n neurons. So it's actually then the bias is then the sum of all the values, because you actually would multiply this with a vector containing ones. So we would multiply this as a dot product. So we can just say np sum the values. Of course, along the rows. And that's it. So that's our backward part for the dense layer. So again, here's just a reminder that the inputs, that will be the values for the next upper layer, because the first layer feeds in the output in the second layer, which is the input of the second layer. So therefore, we need the feedback from the second layer to the first layer. So we're gonna do the same with the relo. So we have our forward part. Also here, we need to remember the inputs. Why? Because the derivative of the redo part is actually pretty simple. So we just need to multiply the values either with 0 or with 1. So just want to remind you on that the relo has this particular shape. So the derivative for negative values is 0, and the derivative for positive values is 1. So therefore, we just look for all these inputs which are negative, then we set them to 0, and we multiply the outer derivative with the inner derivative, which is just 1. So we just leave them as they are. So the only thing that we have to do is that we just take the values and then just check where the inputs were negative, set this to 0, and that's our d inputs, which will be the d values for the next layer. So that is actually pretty simple. And before we go and calculate the cross entropy, we just like to implement this in our code. So we just go back to the relo. We just need to remember the inputs. And then we just define the backward part. Again, same idea. We feed in the d values. That comes from the layer below, so it's the outer derivative. And then we have to calculate the inputs, which is required for passing on to the next layer, which is above the relo layer. So we just say self the inputs. And we just can calculate this by taking the inputs themselves. We want to create a copy. So we just, sorry for the values. So we do this by just copying the t values. Okay, so we just copy the t values, then just remember what the redo function looks like. So for negative input values, the slope is 0, so that has to be 0. And for non-negative input values, the slope is 1, so we can just leave it as it is. So if you multiply these values either with 0 or with 1, so we can just say self the inputs, and then we just go into this vector and say, well, if self inputs is negative, then we have the indices where that is true. So therefore we just multiply this, or we just set this to 0, and we just leave the rest as it is. Yeah? So that's the inner derivative. So that's actually multiplying the inner derivative with the outer derivative. Either it's we multiply this either with 0 or with 1. So we just set the negative values to 0. All right, so the next step will be a bit more complicated. And we have to take a closer look. So we have to do the same thing now for the entropy part, where we calculate the cross entropy, and also for the softmax layer. Let's start with the entropy. So remember, we're calculating the cross entropy, where we multiply the true class with the prediction, with the ln from the prediction. And of course, the true class is either true or false. So this is 0 or 1, whereas pi here is the predicted probability for the class from the softmax layer. So let's say we have this expression for each data point, and the cross entropy is the sum of that. So what does it actually mean? So as I said, the true class is either 0 or 1. So this sum is actually just ln pi for this particular class where this is actually true. Now we calculate the derivative, which will be the inner derivative now. And the derivative is, of course, with respect to the pi, because the true class, it's constant. So and if we calculate the derivative, we just have the ln pi, which gives us then the derivative, which is p true divided by the probability which we get from the softmax layer. And if we do this for all observations, for all data points, we will get such a vector, such a gradient of the entropy. Okay, so that's actually not a big deal. So that's relatively simple, and we can kind of calculate the gradient for the entire sample. So we, for example, can divide it by the sample size later. We have now our function where we calculate the cross entropy, and also here we have to add now our backward part. So let's say we get our d values, and of course we have to compare the predicted probabilities with the actual probabilities. So again, we want to make sure that we have the right shape or the right structure of our class, whether it's encoded in sparse vector, then the shape has the length 1. It just has just one dimension, so to say, or just one extension in one direction. Or it's a one hot encoded matrix, and then length shape would be 2. So we have to make this decision. We have to include an if loop, and then we have to turn it into one hot vector. And we can actually do this with the operation I. Let me also just quickly show that how that works. So I therefore want to go back to the previous screen. So in the last section, I showed you a little Python function which can turn our vector y into one hot encoded vector, one hot encoded matrix. And in principle, we could call this matrix now at this function all the time when we want to apply our backpropagation part. But that's very inconvenient, and that really takes time and always calling this function. So that actually would work kind of, but would make the code really slow. And luckily, Python has these nice tools where we actually don't need to do that. And that's NPI. So how does it actually work? So we have a certain number of labels, which is 3 in our case. To just remember, we have NP unique of y. And then you see we have 3 different classes. And if we just say NPI with our 3 different classes, then we just get the identity matrix. And the trick now is if we apply our vector, our sparse vector y, then we automatically get the one hot encoded matrix. So again, the function I showed you earlier would work. We could actually use it, but we don't want to call this function every time we run our backward method. And that would really slow down the code. Therefore, we're just going to use these Python internal functions. And also the code looks a lot shorter. So that's why we want to include this NPI now. Okay, so then we have our one hot encoded matrix. And then we just calculate the derivative of the entropy. Remember, that was the true class divided by the predicted class. And then we also kind of normalize it because we want to have at the end, we are calculating the total loss. So we calculate something like the mean loss. We just divide by the number of samples. Okay, so that's the entropy part. And now let's take a look at the softmax. And that's where it becomes a bit more complicated. So let us remember the equation. So that was the Boltzmann distribution. So the softmax layer essentially is just the Boltzmann distribution. So the epsilons were the output from the last layer. And I now denotes every class or category, and J denotes every observation. And then we normalize the exponential value of that according to the Boltzmann distribution, and then we have the probabilities for every class I for every observation J. So we will have these I values for every observation. In our case, for every observation, we have 3 different classes. So I goes from 0 to 2 if you count like Python. So we have 3 different classes, and then J goes from all the different observations. So we have to calculate the derivative because that's the inner derivative now. So we have to calculate the derivative of Pij with respect to epsilon because that's our inner derivative. So let's just pick one particular class, K. And now we calculate the derivative of this expression with respect to epsilon of a particular class K. So then we see that the derivative will actually split up in 2 parts. So we just apply the product rule because we have the exponential multiplied with in the denominator. So that's the sum to the power of -1. So we just apply the product rule. So we will only get, so if we, for example, and apply the product rule, we just leave the second factor as it is and only calculate the derivative of the first factor. This gives us 0 unless our I equals K. And then we have to calculate the derivative of the exponential, which gives us the exponential. So we leave this part as it is. Then we have to calculate the derivative of the denominator. So we leave the first factor as it is, then calculate the derivative of this, which is the sum to the power of -1. That gives me a -1 of the other derivative. That gives me a -2 then. So we have the sum to the power of 2 in the denominator times the inner derivative, which again is the exponential. In this case, this is never 0 because in the sum, there will be always this particular class or category we calculate the derivative from. Because remember, K is a member of I. So I goes, in our case, from 0 to 2. So we have 0, 1, 2, and K is one of those classes. So therefore this part here is never 0. You always have this epsilon Kj, whereas this part can be 0 if our I is not this particular K. So we have 2 cases then. So first of all, we can kind of rearrange this equation a bit because we see the same structure here and the same structure here. So we have the Boltzmann distribution here again and here again. So we can just say this is then Pi, Pkj, and this is Pij. So we have these 2 cases then. If our K equals I, then this part is not 0. That's where this 1 now comes from. But then we have epsilon K. So that's why we have a Pk. Here, that's always not 0 because in the sum, there's always this particular epsilon I, which is an epsilon K. And that's why we have a Pi here because that is always true. So no matter what this K is, we always will have this part in the equation. If that's not the case, right, then again, this part here is 0. So we'll only have, so this part disappears, and then we will have just the product of this. If that was too fast, or if it's not really clear to you, I really recommend to really write it down on pen and paper. Then you easily can see that we actually have these 2 cases. So we have now 2 cases, or two different equations. So either we have this particular class K, or we have any other class. So we have different parts of an equation, but we still want to write them in one equation. And one possibility to do that is to use the so-called Kronecker symbol, this little delta ik. It just is a prefactor, so to say, or just a factor which is either 1 if I equals k, or it's 0 if I does not equal k. So it's actually not a function, it's more like a symbolic writing of this equation. So therefore, we can now combine these two equations here. So again, we have both components if I equals k. We only have this product here. So the second part of the derivative, if I is not k, and if, so the first part is 0. So now we can combine it. And then we have also the first part here with the Kronecker symbol. So that's the complete equation now. So that was the first part in the derivative, and that was the second part in the derivative. So, and therefore, we have now, we found a method to write down our derivative as one equation, and we can apply this to our code now. So, but let's take a look at this. So what does it actually look like? So we have our output from the softmax layer. And let's say we have this particular output for one particular observation, J. So for the first class, we have the probability 0.3, for the second 0.6, and then 0.1. So how would it translate into our equation then? So if we have our equation above here, then we see that we actually can have all kind of mixtures, right? We can have this expression here with these three classes, and we have the derivative with respect to class number 0. Then this gives us a value, this gives us a value, and this gives us a value, which is here in our recipe. And we can do the same thing for class 1, so this class, and then we can do the same thing for class 2. So remember, k is, so goes from, can be I equals 0, I equals 1, and I equals 2. So for every data point, we have these three derivatives. So if we have then three classes, we will have the derivative for this, and for this. And every time we will have this equation. So we will have a matrix, and it's a number of classes square matrix, yeah, because we have the mixed derivatives. So our matrix then actually, so for one particular observation, then looks like this. So the first part is only not 0 if I equals k. So that is just a diagonal matrix, right? If I equals k, then this is not 0. The second part is never 0. So we just multiply eij with pkj, on these k's go from 0 to 1 to 2. So what we just do then is we just multiply this row. So we just, so to say, multiply this matrix with itself. It's what we see here. So we multiply this column with this row, which gives us 0.9. Then we multiply this column with this row, which gives us 0.18. This column with this row, that gives us 0.03. And then the next step in the matrix multiplication, we would multiply this column with this row, and it gives us 0.18 and so on. So I think it's clear now. So if you really write this down with 3 or 4 different numbers, then you really see that you will have this matrix here, because we have now all the mixed derivatives. Yeah, because again, the k can be any of those classes, of those 3 classes, and that's why we have a square matrix. This matrix has a name, by the way. It's a Jacobian matrix. So every time you have a square matrix of these mixed derivatives, it's called the Jacobian matrix. So we can also, there's also a simple way how to do this in Python. So what we have to do now is the following. So we have to convert our probabilities into a diagonal matrix where only the diagonal entries are non-zero. And there's a function for that in in Python, it's called diagonal flat. So we just take the output of the softmax layer. And remember, this is just for one particular data point, right? So this is just a vector. And the entire softmax output, however, is a matrix. So this is just one row of this matrix. And that turns into a square matrix. So again, every data point is just this particular row. And due to these mixed derivatives, this row now turns into a square matrix. So we have the diagonal matrix, which we can create with this command here. And then we have this, the matrix, the square matrix multiplied by itself. So we just say softmax output times softmax output, because that's just multiplying the matrix with itself according to the equation we derived. So this operation is only for one data point, and we have to do this for all the data points. So we're going to run this in a loop then. Yeah, more compact ways to do that, but we want to stick to this loop that you really can see how we can calculate these mixed derivatives step by step. So this is for one particular point j, and we have to do this for every point. So for every data point, we have to calculate the Jacobian matrix, and that actually puts us to an interesting problem, because the idea is, of course, that we have to return this inner derivative in our layer and multiply this with the d values and return this to the layer which has been above the softmax layer. So the shape of the matrices have to match. So, but the thing is, what we get now, or what the softmax layer produces, is a matrix, right? So we have, for every data point, the different probabilities for the classes. Now we calculate these the derivative for the probabilities according to the equation we just have derived. So it's just a derivative of the Boltzmann distribution. And as you have seen, for every data point now, so for every row, we obtain an entire matrix that turns our 2D object into a 3-dimensional object. That's for every data point, you will have these mixed derivatives, which will be this, the sum of these two matrices, right? The diagonal matrix and the squared matrix. So then we have such a 3D structure, but what the structure we need to have is actually a 2-dimensional object that we have to feed in back to the last dense layer. Because remember, from the last dense layer, we get all this output that we turn into probabilities. And in the backpropagation part, we have to do quite the opposite. So we have to feed in the output from the backwards part of the softmax layer as the inputs into the last dense layer. So we have to have this flat object. And how do we actually do that? That actually always gives you a hint of how to arrange these matrices that they still make sense, right? Because you have to feed an object back that has the same dimensions here, the same structure. So how do you do that? Well, the only way how to do that actually is to have a dot product of these matrices with the d inputs. So whatever the inputs or the d values are, it has to be a vector that I multiply with every observation. So for every observation here, the d values have to be a vector, and I multiply this vector with the Jacobian matrix, because that will return again a flat 2-dimensional object. It's interesting to note actually that if you just look at such a column that's highlighted here in green, this would be just the entry, so the probability of one particular observation for one particular class, right? The observations are along the different rows, and the probabilities for the classes along the different columns. So this would be the probability for a class of a particular observation. But since we calculate the mixed derivatives, then all the other probabilities have an influence on this particular probability. And it perfectly makes sense because all these probabilities just sum up to 1. So if you just change one probability for one class, it must have an impact on all the other probabilities because the overall sum has to be 1. So it fully makes sense that we have this matrix with the mixed derivatives. So just from the logic. And again, we have to turn this box, so to say, into a two-dimensional object. And the only way how this works is that we multiply these matrices here with a vector so that according to the matrix multiplication, I will get a 2D object back. So whatever the D values are that come into the backward part of the softmax layer, it has to be a vector for every observation. So then we just multiply the Jacobian matrix, which was the inner derivative, with the outer derivative. So whatever this is, wherever it came from, which are the D values, and then we will have such a flat structure again. Again here, it really helps to write this down for a few observations and do the math a bit. That really becomes clear what we have to do. But always think about the shape of these matrices and the orientation. And then even actually without knowing what you're doing, kind of, you know how to put it together. Because just the dimensions have to make sense and they have to add up. All right, so therefore we have to include this in the backward part. And I just want to show you what we have to do. So as I said, we have to multiply for every single observation, we have to calculate, first of all, the Jacobian matrix. So we get the output from the softmax layer, which is just a vector. For every single observation, we just have a vector. Then we calculate this diagonal matrix. And we subtract this value by the squared matrix, which gives me the Jacobian matrix for this particular observation. But then we have to calculate the dot product or the matrix product of this Jacobian matrix with the D values of this particular observation, which is a vector. And this gives me back a vector again in D inputs. And I get this for every observation. So again, I will have a two-dimensional matrix. And it has to align a bit, so I have to reshape it. And of course, we have to run this in a loop. And there's a clever way how to do that. So there's enumerate in zip, and that might be something you're not 100% familiar with, so I can show you this in the code. But first of all, this will be the structure for our softmax layer. All right, so I think I would now just go back to our screen and to our user interface, and I would just quickly want to explain a bit what zip in enumerate means. So when we want to calculate the product of the Jacobian matrix with the D values in the loop, so we're going to use the commands zip and enumerate. So first of all, what means enumerate? So just take a look at the, or just want to give you a very simple example. Let's say we have a list. And let's actually write letters in the list. So like this, so like A, so like just characters. That I can prove the point, so to say, and just have arbitrary characters. So how works? So how does a loop in Python generally work? So you just say for L in L, and we can just say print L, and what we get is the content of L, which is actually pretty useful. But sometimes you also want to have the index. So you could actually just include something like or add something like a counter, but there's another method. It just says, then you can just say enumerate And then you will not only get the content, we get also the index. So let's print both. Let's print the content and let's print the index. So I print the content, which is L, and I print the index, which you can see here, which is I. And I can also have two lists, right? I have, for example, another list. And let's give the other list other characters, like C. Yeah, X. Yeah, W. All right. So, and you can also just say or evaluate both. So we can, for example, just say you have the output L1 and L2, and then you can evaluate both with the command zip. And then you can evaluate both lists. And you can combine this with enumerate, and that's what we are going to do. All right, so now we have all the prerequisites for writing the actual code. And before we do that, I would now stop the section here and continue with the second part of the section.